All right, we are at 36.5, interference in thin films. Let's dismiss my image and continue on. They start off with soap bubbles, and I'm sure you've seen soap bubbles, and you've seen these very beautiful, almost dancing color patterns in a soap film, and it changes over time as uh, the thickness of the bubble changes as it's about to pop. You also see it like on a thin film of oil that's uh, on top of like a wet road. So let's study why this is. Yeah, so you have interference in light reflected from a thin film is due to a combination of rays one and two reflected from the upper and lower surfaces of the film. So you have now these rays that they're showing you have quite a bit of angle, but in reality, these are rays that are almost normal to the surface. They just expand it here so that you can see, so that they're not one on top of each other, and you can see them better. So let's remember that these angles are nearly normal to the surface. So you have air, which is an index of refraction of one. You have the film, which is some higher index, maybe 1.2, 1.3, and then back into air, so, 1.0. So this ray one, it's reflected off of the outer surface of this film, and there's a 180-degree phase change because going from a lower to a higher index of refraction. The ray continues on inside the film and is reflected off the backside. Well, on the backside, you're at your higher index of refraction to a lower, so there is no 180-degree phase change, and so it travels t and 2t. It travels twice the length, and it comes out as ray two. Um, Now we can look at this. So one and two are reflected rays. Three and four are transmitted waves. Ray three and four lead to interference effects for light transmitted through the film. So, oops, I went too fast. Uh, Lambda over n, the wavelength within the film here, is equal to lambda over n. So the for constructive interference, you get that 2t, this length here, 2t, is equal to m plus 1 half lambda over n, and m will be 0, 1, 2, and so forth. Now, we can substitute this lambda over n in for lambda n. If we do that, we'll get 2t equals m plus 1 half lambda over n, which if we move the n to the other side, we'll get 2nt equals m plus 1 half lambda. Now, again, this is for constructive interference. For destructive interference, we get 2nt equals m lambda. Now, this is for the situation where you're going from a index of refraction that is lower uh, to a higher, and then a higher to a lower. Now, let's say this were air and this were a film, some kind of protective coating, and this is a glass lens. Uh, it would be different because you'd get 180 degrees phase change here and 180 degrees phase change here. So it reverses the situation, and that's something to remember. Um, okay, one microscope slide is placed on top of another with their left edges in contact, and a human hair under the right edge of the upper slide. As a result, a wedge of air exists between the slides. An interference pattern results when monochrome light is incident on the wedge. What is the left edge of what is at the left edge of the slides? Let me catch up to my notes. Well, it's a dark fringe. Um, the It's a dark fringe at the left edge. The air wedge has zero thickness, and the only contribution to the interference is that 180-degree phase shift as the light reflects from the upper surface of the glass slide. Okay, and let's see. Newton's rings. Newton's rings. This is almost akin to the two glass slides. If you take this you know flat and spherical lens, you've got you go from this uh, you're getting reflection here, reflection off the bottom, the no phase change here, but from here you get a phase change. So you get interference patterns, and you get these Newton's rings, what are called Newton's rings. We won't go into much more discussion about that. And then we're going to talk about iridescence. Now, the iridescence on things like hummingbirds and birds and butterflies is not necessarily pigmentation. Let me do a new share, and I'm going to show you a slide. Let me see if I can find it. Here it is. This is from a article from Physics Today. Um, let's see, this is June of 2015. I'm going to read you this little paragraph here. Many butterflies get their color from some arrangement of the structural elements sketched here. The array of circular windows, that's these circular windows here, the array of circular windows in the base layer, the diffraction grating of struts, these struts arising from the base, and the tree-like stacks of ridges protruding from the struts. So it's an optical effect from the structure. It's not actually pigmentation. It's not from the pigmentation in the butterfly wing or the bird wing. You get these structures that cause these optical effects. So let's go back to um, the PowerPoint, and there it is. And I think that that ends the. Oh, let's see. Just the discussion on um, how to the problem solving strategy, conceptualize, think about what's going on physically in the problem, identify the light source and the location of the observer. Then you categorize it, confirm that you should use techniques for thin film interference by identifying the thin film causing the interference. Let's analyze. You can The type of interference that occurs determined by the phase relationship between the portion of the wave reflected at the upper surface of the film and the portion reflected at the lower surface. The phase differences between two portions of the wave have two causes: the differences in distance traveled by the two portions and the phase changes occurring on reflection. Remember, from a lower to a higher index of refraction, you get a 180-degree phase change. If you go from high to low, there is no phase change. Um, Now, both causes must be considered when determining which type of interference occurs. If the media above and below the film both have index of refraction greater than that of the film, or if both indices are smaller, so you have to take these into consideration. Use the equation shown for constructive, the second one for destructive. If the film is located between two different media, one with n greater than n of the film and the other with n uh, greater than the I'm sorry, if the film is located between two different media, one with n less than the index of refraction of the film and the other with n greater than the index of refraction of the film, reverse the equations for constructive and destructive interference. And then finalize, inspect your final results to see if they make sense physically and are of the appropriate size. And with that, that ends our uh, section 36.5 discussion.